Solubility. I've already covered energy in another video, so this one will just be on solubility. So what happens to the amount of sugar that can be dissolved in water as the temperature of water is increased? Well, if we compare iced tea versus warm tea, we all know that we can dissolve more sugar the warmer the solution is. To a limit, of course. There is a limit, and that is represented by the solubility. Define exo and endothermic. So endothermic means that a reaction absorbs energy, or energy enters the system. Something that is exothermic releases energy, meaning that energy exits the system. So what is solubility? Solubility is defined as the maximum amount of solute that dissolves in a given quantity of solvent at a particular temperature. Solutes can be insoluble, meaning that less than 0.1 of a gram will dissolve in every 100 milliliters. So there is a small amount of dissolving when something is insoluble. It can be slightly soluble, so between 0.1 and 1 gram dissolves in 100 milliliters of solvent, or it can just simply be soluble. Greater than 1 gram dissolves in 100 milliliters of solvent. What you need to know is on the back of your periodic table, things are listed as very soluble or slightly soluble in our solubility table. Okay, so we have very soluble, which when placed in water, that means those things are going to be aqueous. And we also have slightly soluble, which means that when placed in water, those things are for the most part going to be a solid. But it does mean that although most of it is a solid at the bottom, there are a few particles that are dissolved in the solution. Not enough to make any major changes to things. However, we should note that there are a small number of those particles dissolved. So a few things that we can generalize when we're looking at solubility of a solute in water. So we're talking about a solid solute in water, a gas solute in water, a liquid solute, and an element as the solute in water. We know that if we increase the temperature, a solid solute will, the solubility of a solid solute will also increase. The generalization for a decreasing temperature is that, of course, our solubility will decrease. And the example here could be tea. A gas, as I increase the temperature, think about pop, the carbonation in pop. As I increase the temperature, the carbonation in pop decreases. Okay, because the solubility of the gas in the pop decreases as well. All right, the gas molecules get more energy, and that energy takes them out of the solution. As I decrease the temperature of a gas solute in water, the solubility of that gas solute increases. I slow the particles down, and they are able to remain in solution. So the example here could be pop. Let's quickly talk about pressure. Let's continue with that gas. As I increase the pressure on the solution, so it would be like a closed container, and I increase the pressure here. Remember, our gas solute, most of it might want to be dissolved, but some of it is out of solution as well, because gases, the particles are still moving. As I increase the pressure up here, it forces these molecules into solution. So if I increase the pressure, the solubility of a gas in water increases. And vice versa, if I decrease the pressure, I give it more room and it pulls some of these molecules out of water. Now, solids are really unaffected by pressure. So if there was some solid at the bottom here, increasing or decreasing the pressure up here is not going to have an effect, because solids are unaffected by pressure. All right, last one, second last one, a liquid. A liquid is unaffected by temperature and pressure because typically a liquid is molecular. So it's unaffected or unchanged by an increase or decrease in pressure. This is because liquids are simply miscible, meaning they can mix in any proportion. The reason is, if we think about oil in water, it doesn't matter what I do to the temperature, oil and water will still never mix because we have a nonpolar and a polar liquid. Okay, same thing if we had two polar things, let's say orange juice, so OJ and water. It doesn't matter what I do to the temperature, these will always mix in whatever proportion I add. Okay, same with pressure. Pressure does not affect this. Unaffected. Because again, liquids are unaffected by pressure. So the only one it seems we can control is a gas. And liquids are mostly molecular, and it's based on polarity that allows them to be soluble. Last one, an element. Elements are typically unaffected as well because they are usually non-polar if they are like diatomics, or they are metals. And so we know that I can't really dissolve a metal in water, so these are unaffected as well. They do not have solubility. So really what we're looking at is solids and gases and their solubility in water. Remember, a solid, really only temperature is affecting it, but a gas can be affected by temperature and pressure. A saturated solution is a solution that contains the maximum amount of dissolved solute at a given temperature. So the solution is full. I can't dissolve any more. If I add more solid, it is not going to dissolve. It is going to sit at the bottom. So a saturated solution can be recognized only when there is undissolved solute. So I don't know that something is saturated until I've added and there are undissolved particles at the bottom. Okay, no matter what I do, I can't get them to dissolve. So we don't know until there's some sitting at the bottom. When you study that saturated solution, remember, with particles or solute at the bottom, the amount of undissolved solute at the bottom remains unchanged. So I don't see that all of it got dissolved, but then 20 minutes later, there's solute there. It stays the same throughout. However, over time, the undissolved particles become dissolved and the dissolved particles precipitate out of solution. So it's not that everything is unchanging, it just appears that way to our view. So in an unsaturated solution, meaning more solute can dissolve, what we see is if we put the solid into our solution, lots of it is going to be dissolving, okay, or becoming aqueous. What we do know is that a little bit of what became aqueous will also precipitate back. So the rate of precipitation versus dissolving is different here. So it will dissolve, the dissolving rate is greater than the precipitation rate in an unsaturated solution. In a saturated solution, remember, our solution is full. It's got no more room for solute particles. So when one solute particle dissolves from the undissolved solute at the bottom, a dissolved particle must precipitate. So in a saturated solution, the rate of dissolving is equal to the rate of precipitating, so that this mass is unchanged. Whereas over here, this mass will decrease as these particles dissolve into solution. A way of thinking about this is a full or an empty-ish bus, okay? So on a full bus, like I'm thinking city bus, we have people standing and we have people sitting, okay? When somebody gets off the bus, typically somebody gets on the bus. So we have somebody who stands up from their seat and somebody who will sit down in that seat. All right. So there's always this transition from the number of seats that are full. We'll keep the seats full, but it's not that the people who got on the bus at the beginning of the route are the exact same people still sitting at the end of the route. All right. Over here, we have lots of room, lots of seats. Sorry, this looks a little bit opposite. So as people get on the bus, they are going to immediately sit down. There may be somebody who stands up, maybe gives up their seat for somebody, but there'll always be more people sitting down than there are standing up on an emptier bus. So with that idea, a saturated solution is said to be in a state of dynamic equilibrium. Equilibrium occurs when a process, like dissolving, and its reverse process, like crystallizing or precipitating, take place at the same rate in a closed system, meaning that we're not allowing water to evaporate because that would change things. So like in a closed container. So we can represent this for a solution. So let's use sodium chloride. So when sodium chloride dissolves, we start with NaCl, which is a solid. We place it in water and we note that we get Na as an ion and Cl minus as an ion. Crystallizing or precipitating, whatever you'd like to think about this as. Probably crystallizing is the better word because we're not adding a new compound to make it precipitate, if you will. What we're looking at for crystallizing would be the Na plus ion in solution coming together with the Cl minus ion in solution to make NaCl as a solid. All right. So dynamic equilibrium, the equation would be, typically we write like our first one. It doesn't matter which one you write here. We say that we are, of course, getting the dissolving, but we are also getting the crystallizing. So we just add the arrows both ways. Of course, this is the exact same process, just opposite. So this equilibrium arrow, which again is two arrows or sometimes just written like this, never like this. This means something different in chemistry that we don't talk about, but we don't use a double-ended arrow. So using these two arrows, it means that the process can go in the forward direction and in the reverse direction. Take a look on our website for practice from the Nelson textbook. This was the McGraw-Hill.